So, adjacency matrix. So this is an example of an adjacency matrix, the same map that we had previously. Remember, we had, where is it now? Somewhere up there. There. For that map example that we had. So now we set up a two-dimensional array, or matrix, with the nodes on both axes. We have a node on the, we have an axis on the X side, on the left side, and on the top side, and each one of these axes then contain all the nodes. So keep that in mind, and then look at that two-dimensional structure here. All the nodes are listed on the left, and all the nodes are listed at the top. And then in the cells, we have the weights or the distances, if there is an edge from U to V. On the left-hand side, we have U, at the top we have V. And convention says edges run from U to V. So if there's an edge from Bloemfontein to the Wetstop, at the very top you see 70. If there is a reverse edge from the Wetstop to Bloemfontein, you see 70 as well. So the two triangles, the upper right one and the lower left one, indicate two different directions. Bottom left triangle is from U to V, top right is from V to U. And we enter the weight in there, if there is a weight. If we do not have a weighted graph, if we are only interested in whether there is an edge or not, then we just enter a 1 in there, so that it's not empty. Then each one of those cells will be a 1. Depending on your scenario, you might decide to enter a -1 in the empty cells, because depending on the scenario, a 0 might be a valid weight for an edge. There is an edge and the weight is 0. Could be. And then it would not help to enter 0 in the empty spot. So we, in that case, will then enter a -1. Another possibility is to enter int.max value in those cells. So we have an adjacency matrix that we set it up like this for each one of the edges. Actually, this is also a list of edges implementation. And the methods that we have in this implementation is very much the same as that of list of edges, and many of them are the same. So if we now go to the implementation in Visual Studio, sorry, it's that one. That one, yeah. Then we have a node class. And if you compare this node class with, let's say, this one that we had previously for the list of edges, it's very much the same. I can just make this one a bit bigger. That one, now my borders are gone. There. That one a bit bigger. So compare the edge class in this on this side of the list of edges with a node class on this side, where we have now an adjacency matrix implementation. As always, our implementation is generic, so there's a T there, and that T will then be the type of the thing that we actually want to save in the graph. So in our case, we want to save a value, whatever it is, and that type is T. And that's actually all. Line 14, the key value field is not really necessary. We only need that when we want to do the algorithm for minimum spanning tree. MST, minimum spanning tree, which will not be included for the exam. If you want to do that, then you need that field. Otherwise, you actually don't need that one. So it's a very simple embedded node class. We only have the value of type T and then the constructor that assigns the parameter that comes from the class user to this value T. So this is simpler than the previous implementation of the embedded node, but we have a more, it's not complex, but let's say it's a bit more complex than the previous side when we have the private data members. You will remember for the list of nodes, we had an array of nodes. That was the list of nodes implementation. And we had a size property, which will just return the length of that array. And that's the same here. But now we have this. So instead of saving the edges in there, as we have done before, we now save an adjacency matrix. That is a two-dimensional matrix. In this case, the type is int. It can be something else, double. But in this case, the type is int. In our example case, we might use this class for implementation of a map. Remember that we are developing a generic class, and it's not always used for a map, but it can be used for a map. And in that case, that int will then be the distance between two towns. And we have a two-dimensional array, because we have that matrix as we have just seen it, and we have two dimensions. So, and by convention also, we refer to this two-dimensional array with the letter M. You can use something else for it, but we have an M there. And then the constructor of the graph will instantiate the array of nodes, initially 0 elements in that array, and that node array will be resized as we add vertices or nodes. And then in the constructor also we instantiate the adjacency matrix, again with 0 elements in each dimension. And that will also be added as we go on. So that is the basics of the adjacency matrix implementation. And you can put the other two next to it yourself to compare and make sure that we understand the differences between them, especially regarding the embedded node and the private data members. Compare those between the three implementations of the graph class. So for now, I will make the adjacency matrix implementation bigger and focus on that one only. So the next thing that we have to have a look at, first thing that we need to do in any graph is to add nodes. Now, it's actually quite simple. First of all, we resize the array of nodes and then assign a new node to the last spot in the array. So that's the first step. But we also have to resize the adjacency matrix. Now, that is not that simple, because unfortunately there is no array.resize built-in method in .NET for two-dimensional arrays. The array.resize method is available for one dimension, and that makes it easy to resize an array when we have one dimension only. If we have two dimensions, the array.resize doesn't work, and we have to do something else. So what I regard as the easiest, and there are other methods, and you can Google and you will find algorithms to do that. In other words, you resize in place. Take the existing array and resize its size, making space for extra elements. But the easiest way to do it actually, and I've done it here in an extra separate private helper method, is in 4 steps. We create a temporary array locally of the existing size, the existing M adjacency matrix size, and those that get length method returns the length or the number of elements in dimension 0, and then get length method returns the number of elements in dimension 1. So we create a new temporary array the size of my existing adjacency matrix. Then I copy all the elements in my existing adjacency matrix M to my new temporary matrix. So in line 54 to 55, it's a nested loop. One loop goes to one dimension, other loop goes to the other dimension, and then in line 56, we assign the values from the adjacency matrix specific position ij to the temporary matrix that we've just created, ij. And then in the next step, we create a new M. So we overwrite the existing M. Create a new M with a new dimensions, new size. And then we copy the elements back from the temporary array to M. Just the reverse of what we've done in step 2. So this we need to do every time that we add a node. We have to resize our adjacency matrix. Note that we have resized the adjacency matrix. We have not yet entered the value of an edge. We did not create an edge. We just made provision for possible edges. There's no edge yet defined between one of the existing nodes and the new node that we have just added to the graph. So this is add node method. And then if we want to add an edge between two nodes U and V, note that this is public. So this is called from the class user. If we go to the class user, called graph method there, I add nodes and I work with strings. So my graph, the T is a string. And I add my nodes one at a time. Every node in the map is added like that. And then I start to add edges. And I add an edge from U to V of a specific length. So there's an edge between Bloemfontein and Tabanshu, between Tabanshu and Tweespruit, between Tweespruit and Ladybrand, etc., etc. So the class user will add the edges in this way. And then when we go to the graph class, of course, now Bloemfontein sits in U and Tabanshu will sit in V, etc., etc. The weight, the 80 kilometer, will sit in there. And then, first of all, we cannot add an edge if the nodes do not exist. So we just check, do the nodes exist? If they do not exist, then we have to add them. So we do that implicitly. So actually, we do not have to enter, we do not have to do this part. We can actually just ignore that and take it out. Because those nodes are added implicitly when we add an edge. Note also that the things in the graph are of type node. But the thing that the user enters is the string of the town name. And that's two different things. We have nodes in the graph, but the user is not interested in the overheads, what's going on in the background. The user just wants to enter Bloemfontein or Tweespruit or whatever with the distance. So when I check if a node exists, I have to take the U, which is of type T, and use that little part of link to convert it to my nodes, which is of type node, to a list of T, and then make sure that it contains it. I cannot just check if U is inside the node because I will get a type error. U is of type T, nodes is a list of node, so they're not compatible. So I have to do this little thing to map my list of nodes to a list of values. So I do that for both U and V, add if necessary. And then next thing that I have to do is to get the indexes. Now again, note our convention. Capital U is for the node, lowercase u is for the value in the node, and then U underscore will be the index of the node in the list of nodes, or the array of nodes. So I can find the index and work with that further. It might make it a bit easier, and that is actually necessary because I need that index when I access cells in the adjacency matrix. I cannot access cells in the adjacency matrix without that index unless I have an indexer in my class. So get the index and take that step by step again. Array.indexOf is a built-in array class. Index of built-in method of the array class. And again, I have to do that to map my list of nodes to list of values. Make that an array, and then get the index of U in that array, and then I will get U underscore. So it's a bit of work to get that U underscore. Once I have that, I can now assign a value to one of the cells in my adjacency matrix. Of course, that line 76 and 77 will return a -1 if the node does not exist. Array.index of returns -1 if there is no such index. So I have to check in line 80. I cannot just enter a value in the adjacency matrix. I have to check if my indexes are indeed larger than or equal than 0. In a directed graph, I have to add these two edges separately as two separate edges. And then the class user would have to repeat all this work. He will have to repeat this twice. This one just reversing those two values. But we can save work for the class user by adding an extra parameter. And that true says to the class user, there's also a reverse edge from the Bloemfontein. So instead of expecting the class user to do the work again, we just put in the true there, and then the class itself will take that reverse value there, and then add this edge in the reverse direction. So from V to U. The weight is the same. And of course, you should now put a false in there, otherwise this thing will never stop. You are now done adding the reverse. So just put the false in there. So this is the add edge method in the adjacency matrix implementation. Questions? That makes sense? maybe not now, but if you're studying for the test and you put these 4 implementations next to each other, you can decide for yourself which one is the easiest. Not always necessarily a case of being the easiest. Some of these implementations also depend on the scenario, what you want to do with the graph. But some of them are easier than others. I believe personally that this adjacency matrix thing, intuitively, it makes for me the most sense. For me, this works best on all the implementations. But you can decide yourself. So the next method that we have to attend to, and there I'm walking again, is the remove edge method. So once we've added an edge, we must be able to remove it. Now the same way as before, line 90 and 91 or 91 and 92, I have to get the indexes of the 2 nodes that I want to remove. No, actually I want to remove an edge, sorry. This is remove edge, but I want to remove an edge between 2 nodes. So the class user, and do we have an example? I don't think there's an example here. But the class user will say remove an edge from Tweesprei to Tabanshu or whatever the case may be. And then in there will be the first node, but again, that's of type T. So I need to find the index, and since my array is not of type T, I have to do this. Then I can find the index of, and if both of those do exist, the only thing that I need to remove an edge is to assign a 0 value to that cell in my adjacency matrix. So I actually do not remove anything. The adjacency matrix stays of the same size. You do not remove any. We just replace the weight value with a 0. Or if you decide that 0 is a valid weight, then you might decide to replace it with a -1. Or if you decide that -1 is a valid weight, depending on your scenario, then you can replace that with some other placeholder which will signify an empty cell, such as int.maxValue. And as before, if I want to remove the edges in both directions, the user will specify true, and we will do here a remove edge in line 99 in the reverse direction. So I don't think that is too difficult to understand. So this is the basics of an adjacency matrix. Now, as always, we have to be able to step through my graph. Now, I thought of something this morning when I was preparing. We actually don't need this list breadth first. We don't need the first or whatever traversal algorithm. We do not have to make it difficult for ourselves if we want to just visit all nodes. It's very simple. We have an array of nodes. Where's my array? I have an array of nodes. All that I have to do is to visit all nodes. Step through the array in a normal, simple, very simple visiting of the nodes. So I don't actually need a breadth first or a depth first if my aim is to just list them. But I do need a breadth first and a depth first if I want to list them in a specific order and according to a specific strategy. And then I need this. So this is the list breadth first order of visiting nodes. Now, nothing new yet. We have done this now several times. Nothing new yet. Now I'm going to walk up here. In that we use a queue in line 108. I have a temporary list in line 106. First thing that I do is to, in my temporary list, I add the starting node. Remember, unlike in a tree, in a graph, we don't have a logical or intuitive starting point. In the tree we have a root. But in a graph, you have to specify now where do I want to start my visits from. So the class user says, when the class user calls this first, the class user would specify the node where to start the traversal from. You will specify, I want to start from you. All right? That's not the one that I wanted to find. Oh, where's this other one? Let's break first. I don't find. Sorry. That is the one that I was looking for. The class user will have to specify a node to start from. So that's important. We have a node where we start from. And then, once we have that, we add that thing to the list that we just created. We also enqueue that to the queue, our starting point. And then, as always before, we have a loop that runs as long as my queue is not empty. First thing I dequeue and put this into U, and then get the index of U. And sometime here I will enqueue the value of the children. So this goes through in the same way as we have done before with queues. We dequeue this, so now apparently our queue is empty, but later on we enqueue again before we go out of the loop, so that we enqueue all the children. And the children, or the successors then maybe is a better word, all the successors are all the nodes where the weight from U to V is larger than 0. That's the children. All the nodes from U to V where the weight is larger than 0, they are the children. But, of course, since we may not have cycles in a graph, we have to check. Sorry, I'm saying graph. Since we may have cycles in a graph, it is possible to visit the same successor more than once from different places. And for that reason, we need to check if that node is maybe not already in my graph, and therefore line 1, 2, 3. No, what's it? 1, 2, 2. I need to check. And if that is not the case, then I can add this new thing, the child, to my list of nodes also that I have there, and then enqueue the value of this to my queue, so that in this way I step through all the nodes in the graph in a breadth-first way. I'm done. If I keep on dequeuing and never enqueue, so when the queue becomes empty, we are done. Loop is done, and then at that time we just return this visited list to the caller of my breadth-first method as a list of T. So the next method, let me just say this. This minimum spanning tree is for enrichment. I'm not going to discuss it this afternoon. You can go through it yourself. And there are some links also there to discuss and how it works. So please do it if you are interested. Make sure that you understand that. And then there are two shortest path algorithms. The one is Dijkstra's algorithm that I have entered in here, and there's also the explanation of it. You can follow that explanation here, and my implementation of the shortest path of Dijkstra. That's also not for exam. But this one, the brute force one, is for exam. You should be able to do that. I don't think that is too difficult. It's not always feasible. Actually, it's very seldom feasible. But yes, you should be able to do it. Stepping through all possible paths in the graph and finding the shortest one from U to V. So I have here some helper methods, and this is just me. When you look at the explanations of these things on the web, you might not find these helper methods, but I decided I think it's easier if I have these helper methods, and then instead of calling this long line of code each and every time I need it, I just call this. For me, that works easier. Or the same here. If I want to find a specific node with a specific value, that's one way of doing it. Or you can use this select from link. So I have some helper methods in here, which I'm not going to discuss in detail. You can go through them yourself, or you can implement them in a different way. And they are all, of course, private. So this neighbors method, and there are two neighbors methods. They're all also two private helper methods. Note the difference between them. This one will return a list of node. This one will return a list of T. This one will take a parameter node, and this one will take a parameter of type T. But they will find all neighbors of a specific given node. In other words, all successors, all adjacent nodes of a specific given one. If I say Bloemfontein and look at the map, all towns that are directly connected, you would want to install towns that are directly connected to Bloemfontein without intermediate towns. Those will be the neighbors. So those are helper methods that I will need in my next method. And as I said, the minimum spanning tree and the Dijkstra algorithm is not for exam, but you should be able to list all paths. Now, this paths method, that's public. I want to find all paths from U. If it ends at, doesn't matter where it ends. I want to find all paths that starts at U. So it might be easiest if I put a breakpoint in. Get paths. Let's put a breakpoint in there. 9214. So up to here, I have just created these. There's nothing in there. So if I run, I can't remember what my test was for U. We'll see just now what U is. So U is Smithfield. All right. So I want to create or get all paths from Smithfield. Originates at Smithfield. At the moment, my list of paths is empty. It's created, but the count is 0. If I press F10, where's F10? I go one step further, put my mouse on list paths, and now, oh no, that one, this one. There's 117. Now, even for a small graph, there are 117 paths originating at Smithfield for that small graph. 117. That's small graph. Paths originating at Smithfield. Now, maybe we don't understand, it doesn't seem likely, but let's have a look and list them. So there are 117 of them. Each one of these paths have some vertices. If I open any one of them, Smithfield, Webner, De Wetstorp, Reddersburg, Bloemfontein, that's one possible path. If I open another one of them, what's the time? If I open another one of them, I have Smithfield, Reddersburg, Bloemfontein, De Bansje, Tweespruit, Ladybrand, Maseru, Mafeking, Webner, Sastron. Right? So there are many paths. Towards the end of my list, you will see that I have paths with a very few number of nodes. Let's go to the end. So that one contains only 2 nodes. It's Smithfield and Webner. That one, the very last one, contains only 1 node, which will be Smithfield itself only. So there are many paths, including several possible combinations of nodes originating from Smithfield. So this is what we do here. This list paths list is global in the class. It's private, but it goes from call to call of my get path method here. In this one, I do depth first, because this is get path and there's a recursive call of the method itself. We do a depth first, and as we go along, we add the nodes to the path, and eventually I will add that path to the list of paths. Now reverse it, because when I use a stack, I put it on top and I want it on the reverse, in the reverse order. And then once I'm done, I have a list of paths. Now this list of paths, just understand the type of list of paths. It's a list of a list. Yeah? Make sure that we understand that. It's a list of a list. A path contains several nodes. Then I have a list of paths. That's a list of a list. And then for the brute force shortest path from U to V, it's a matter of stepping through all 117 of these. So I will step through all 117 of them. First of all, I will check if my path contains the end node. If I want to get from U to V, there are several paths from U, not all of them necessarily ending at V. I will have to check that my path has an end node V. And if that is the case, I will check if this path has a lower weight than what previously found. And then that will be my shortest.